Welcome to 5.2 Chords. In this lesson, we're going to talk about two new segments for circles, and we're going to focus a lot on chords. So in 5.1, remember we introduced the concept of a radius. Now in 5.1, we define the radius as the distance between from the center to any point on the circle, right? Another way to think about the radius is a line segment from the center to a point on the circle. Remember, it's a line segment because it is bound by two endpoints, okay? So that was one of these segments we talked about for a circle. Now we're going to learn about two new segments, and then for one of them, we're going to focus a lot on it. So the second new segment is called a chord. This is a line segment with both endpoints on the circle. Okay, so you see here's a chord here, right here. But keep in mind, a chord can be like this. Sorry. It can look like this. It can look like this. It could look like this. It doesn't matter as long as both of the endpoints are on the circle, okay? Then it would be considered a chord. Now the third one is a diameter. This is a line segment bound by two endpoints of a circle and contains the center. So you see here, it is bound by two endpoints that are on the circle, and it contains the center. Another way to think about it, because if you look closely at the definition, line segment bound by two endpoints. Bound by two endpoints of a circle. That should remind you of a chord, where a chord is a line segment with both endpoints on the circle. Okay, so this part of the definition reminds you of a chord. So another way to think of diameter is a chord that contains the center, okay? So there are three segments for the circles, and we're going to focus a lot on chords. So before we get into that, let's remind ourselves of a perpendicular bisector. This is something you learned in the first semester when we talked about the rays, lines, segments, is when we first introduced those concepts. So let's refresh our memory on what a perpendicular bisector is. A perpendicular bisector is a line, ray, or segment that bisects a segment at a right angle. Now what does that mean? Well, if we were given 2 points, A and B, what would be the distance between those 2 points? It would just be this line connecting them. That is the distance from point A to point B. Now what about a distance from point C to line segment AB, right? It turns out that the shortest distance from point C to segment AB would be a perpendicular line, right? Because if we chose something like this, if we chose this green line as the distance from point C to segment AB, this green line would actually be longer than this orange line. Why? Because if you look closely, this forms a right triangle, and this slanted part, this slant, is actually called the hypotenuse of the right triangle, and the hypotenuse is always the longest side of the right triangle, okay? So that is why the shortest distance from point C to AB is a straight line forming a right angle. Now what is this segment called? It's actually called a perpendicular bisector because it meets AB at a right angle, and it bisects AB because it divides segment AB into two equal parts. Okay, so just keep this in mind as we get into the congruent chord rule. So let me zoom out a little. The congruent chord rule states that if two chords are the same distance from the center, then they are congruent. Okay, again, if reading it in writing is a little difficult for you to understand, I also drew pictures for you to understand. So let's look at the first part of the sentence. If two chords are the same distance from the center, right? So here's one chord, here's a second chord, and you see the distance from the center? I label it as 2. Let's pretend it's 2 centimeters. Now, how does this relate to the perpendicular bisector we just talked about? Well, remember the shortest distance from some point to a segment is the perpendicular bisector. So here's a chord, right? And you can imagine it would be segment AB as we had up here. And this is a point, which is actually the center, and it's a fixed point. So what is the distance from this point to the segment or the chord? It's actually the perpendicular bisector. That's why you see it meets at a right angle for both of these, okay? So that's why I wanted to refresh your memory on the perpendicular bisector, because you'll actually see it when we want to represent distances from the center to the chords, okay? So again, looking at the congruent chord rule, if two chords are the same distance from the center, here's chord 1, here's chord 2, they are both 2 centimeters from the center, then they are congruent. So if they are the same distance from the center, then we can conclude that these two chords are congruent, meaning they have the same length, okay? So the converse is also true. Remember, what is converse? This is if we flipped the constituents of the statement. So if we took the first part of the statement, if this, then this. So if we took the first part of the statement and the second part of the statement and we switch them. So if they are congruent, then two chords are the same distance from the center. So that's what it means when we say the converse is also true. So now the converse statement would be, if two chords are congruent, then the two chords are the same distance from the center, okay? And this is going to be helpful when you solve for missing lengths of chords or distances. So let's look at an example. Let me zoom in. They are asking you to find the length of segment CD. Okay, so let's look at what's given already. We're given that chord AB is 7.9, let's say it's centimeters, and we're also given that chord EF is 7.97 meters. So right away, we're given that segment or chord, remember chords are segments, segment AB is congruent to segment EF. Okay? And this is actually so we know that the two chords are congruent. So according to the converse of the According to the converse of the congruent chord rule, since these two chords are congruent, we can conclude that the two chords are the same distance from the center. What does that mean? If this chord is 2.7 centimeters from the center, then this chord is also 2.7 centimeters from the center. So what is CD? CD is equal to 2.7, and we're going to say centimeters. So we found CD, so we're done. Okay.